Hello, I'm Jonathan Schabowski, and I'm a senior architect in the office of the CTO at Solace. I'm excited to talk with you today about enhancing microservices with events, which is really an examination of how being event-driven can provide solutions to the challenges of APIs. So if you remember in the previous video, we talked about the REST request response paradox, and ultimately there were 5 challenges that we really discussed as limitations if you're going to be exclusively API-driven. So this is the last video in this series, and we'll talk about how you can actually use event-driven to your advantage and overcome those challenges. So if you remember from the last video, we had a use case where essentially you had a web application who was going to issue a REST command. Maybe that's a open account type of a command that was going to flow through an API gateway. And before, we basically had our choreographed microservices, A called B, called C, called D. So essentially what we've done is we've reimagined this into a set of synchronous interactions and a set of asynchronous interactions. And essentially what we'll walk you through is how this provides a solution for failure scenarios, poor user experience, poor scalability and resource utilization, that inability that we had to add new services, and why basically the one-to-many pattern wasn't easy. So we'll show how events really provide solutions for those 5 situations. And we'll show you how basically by being event-driven, services are much more autonomous, which reduces the microservices coupling, which we saw as the big symptom of a problem in the previous videos. So ultimately, what I have found works really well is to sort of have a methodology where you use synchronous interactions only where necessary, and you utilize eventing as much as possible. And I think you'll see as we walk you through this series why that would be. So in this case, what we've done is the web app still, through a REST command, calls the API gateway. The API gateway forwards that message on to the first microservice A, which has a REST interface. Maybe as part of that processing, he needs to do some querying of microservice B to pull out additional information out of that NoSQL database. He then writes the updated, for instance, account open state, and then would actually produce an event. So an event is always a historical viewpoint on something that's happened in the system. It's historical. So in this case, microservice A is sending a notification saying that the account's been opened, and he sends that to an event broker. We'll actually talk what an event broker is here in a second. But what you're then able to do is these other microservices, in this case microservice C and microservice D, can act upon that event however they need to, all asynchronously, all out of band from this synchronous communication. And right basically after we sent that notification of account open, we sent the response back. So essentially, the user that's using this web application is no longer being blocked waiting for C and D to happen. That's happening asynchronously. So an event broker is a system that reliably transmits events to interested apps and microservices across environments. So that's basically the definition for an event broker. And essentially the event broker provides a lot of things that you really need for microservices. So if we kind of go back again to the previous video, what we said was applications need one-to-many data distribution. They need the deferred execution pattern from a user experience perspective, and they need reliable delivery because a lot of microservices require the need for eventual consistency. And again, you're only going to achieve eventual consistency if you have reliable delivery. But things that you also want are things like shock absorption. An example of shock absorption, we'll walk through that actually in one of our things coming up, examples coming up. You need replay capabilities. When downstream systems fail, you need to be able to reconstitute state. Then you can replay all the events that have happened in order to recompute that state. You need integration with legacy systems because ultimately legacy systems aren't going away anytime soon. Discoverability is a good thing, even when it comes to event-driven. And you ultimately need to be able to govern this, have access control, be able to monitor, have visibility into really what's going on. And that's exactly what an event broker provides. So now what we'll do is we'll walk through one by one those problems that we had stated in the RESTful request response paradox, and we'll show you how event-driven actually simplifies that. So first of all, again, microservices need to be stateless. States typically persisted into databases, and essentially what you actually need is persistence if you aren't able to process that message right away. And so messaging in an event broker is providing both persistence and some amount of state. So if you look in sort of this paradigm here, where you have basically a RESTful service, microservice B in this case, and you have a REST request reply. Essentially, this client has coupling to the API, and it has failure logic that deals with sort of the different states in which microservice B can fail. Now, if we look at this with an event broker, the same interaction of being event-driven, essentially you fire an event. When the event broker receives that event, he sends an acknowledgement. This acknowledgement just means that essentially the event broker has persisted it such that in the case of an event broker failure, the message won't be lost. Then these different microservices instances can basically ack and knack that message. And in the case of a failure, for instance, microservice instance B.1, that will be retried and routed to another microservice in the case of a failure. So essentially, the event broker is keeping track of who has actually acknowledged or not acknowledged the message. That's an example of being stateful. But if you look at it from a loose coupling perspective, microservice A is unaware if 0 consumers or many consumers receive that message, which is a great example of loose coupling. And ultimately, it keeps that tricky retry logic out of your code. So whereas this guy had a bunch of fault logic as to how to deal with microservice B failures, microservice A only needs to know about what happens if I can't send the message to the event broker. It doesn't need to know the different states and modes of the downstream services which could consume it. And ultimately, the event broker will also guarantee that the events are delivered in temporal order. So where ordering is mattered, the event broker keeps track of that as well. So if we look at that and apply that concept to our failure scenarios, again, we basically walk our way through what happens if a downstream asynchronous service like this microservice C were to fail. Essentially, when that service comes back online or there's another instance, that message will be redelivered to the service so that it's properly processed and again, eventually consistent. All the other services in this, A, B, and D, are completely unaware and continue to process as usual, which is a big key. And ultimately, it decreases complexity. There doesn't have to be sort of that, how do you, who has to roll back what pieces of information because microservice C didn't complete. Essentially, we're relying upon eventual consistency to ensure that at a time in the future, the system will be consistent. When C comes back online, problems resolved, message is ultimately processed. So that is a huge ease of use, ease of design factor coming into play. So the next case was poor user experience. Before, basically this web app had to wait until A, B, C, and D completed in order to get a response back, which meant that essentially your response time was only as good as the worst service that needed to be invoked. Well, in this case, what we did is we implemented the deferred execution pattern. So essentially, we defined what our minimal execution set is, which is basically the ability for A to update an account open into his database. And in order to do that again, in a real world, maybe you have to query a different microservice. So essentially, this area in blue is that minimal execution set. And the set that's in this kind of teal green color, that's the deferred execution set. So microservice C and D can happen offline or after the fact of this minimal execution set. And so really what it enables is a much quicker response time back to the UI because you're not having to wait for C and D to complete. It ensures that states persisted for future processing. So essentially this message that's being fired to the event broker is exactly that state persistence. It allows these tasks to occur in the background asynchronously even from each other, and it supports the concept of long-running operations. So a lot of organizations that we see have many microservices that have to execute when something like an account open has to fire, and some of those things could take a long amount of time. We're talking on the order of minutes to complete, not even seconds. And so the deferred execution pattern lets all of that happen in the background. If something down here were to fail and not being able to process, then sure, you do have to handle that with basically some additional error handling when that event fires. But again, that's a lot easier to deal with than having a user be blocked and have his response time be poor. And if we look at what the actual process is from a total elapsed time, we were at 19 seconds if you were to have A to B to C to D all sequentially with a response versus basically 8 seconds. All of this time certainly will add up. And finally, as we've already discussed, it does allow the parallel processing to happen, and basically any sort of these service failures don't impact user experience. So the third case here is scale and resource utilization and the ability to scale independently. So again, if all of this was sequential and we had a service that was actually kind of slow downstream, you had to basically scale up all of your other services because in a lot of cases they're in a blocked wait state waiting for that downstream service. In this case though, let's say that microservice C is falling behind. Well, if he's falling behind, it isn't impacting D, and it's not luckily impacting A or B because we've been fully decoupled, right? But what we're able to do is just independently scale C regardless of those other services. That acts to both allow you to scale for average load versus peak load, and it allows you to really detect and alert, a slow service based off of, for instance, a queue size growth situation. And services are then also able to be dynamically scaled based off of that backlog. So instead of having to have a whole lot of services scaled for peak load, you only have to scale your services for the average load, and then in the case of an unexpected peak, you can just scale them up dynamically, which again would save a lot of money in the course of a year, especially where you have bursty style use cases, Black Friday events, etc. So if we take that and we apply that to the shock absorption pattern, we've had a lot of customers utilize this specifically for Black Friday events or when they introduce new products. And really the idea is if you were to basically try to in series, in flow, handle all of the different aspects of a given order, for example, you basically would have service outages and downtimes because the load can be so high. So let's say, for example, you're a cell phone manufacturer producing new cell phones, and essentially you come out with a new hot one that everybody wants to get their hands on. So you open up your website, suddenly there's a bombardment of traffic trying to order that new device. Well, essentially, if you're trying to do all the logistics of the order in inventory, the shipping aspects, the billing aspects, all in order to say, essentially, we got your order done, it would bring everybody's systems to their knees, which is just not good, right? So instead, you implement the shock absorption pattern, which is, again, utilizing the deferred execution case. In this case, let's say that you've got a rate of 1,000 requests coming into your API gateway. Microservice A and B all need to be able to be scaled in order to handle that. But these backend systems, like I said, maybe it's shipping, maybe it's inventory management, maybe it's billing. They only have to be sized for what they typically do. Because sure, the event broker will receive a backlog and keep queuing up those inbound orders that are coming fast and frequent. And ultimately, these downstream services, you maybe only support 200 messages per second. Eventually, they'll eat through that backlog. Everyone's order will still happen, but you're able to handle a lot more traffic and a lot more load than having to scale everything and including your external dependencies up to support these kind of shocks. So that's why we call it the shock absorption pattern, is the event broker is really the shock absorber, and it's absorbing the shock for these other asynchronous services. Again, we have a lot of cases where this has helped a lot of big customers that you probably place orders on pretty frequently. So case number 4, adding new services. Let's say that we wanted to add a new microservice E. Essentially because none of these services actually know about the existence of each other, there are no code changes required to any of these services. Sure, microservice E does still have data level coupling, but that's really about the large amount of coupling that happens. Resource utilization, scalability all remains the same. User experience remains the same because the addition of this new microservices is in that deferred execution group. And ultimately, it's really providing a lot more agility than if you were to add microservice E, which is an API that C has to call out E that then calls D. It just becomes kind of a nightmare if you were using APIs exclusively. Another interesting interaction style here is the ability to turn REST API interactions into events. So if you think about it, a request reply command, let's say, that may be a request reply between two entities, in this case, really between the web application and microservice A. But to another system, that actually you could extend the event broker to actually proxy those services and actually siphon off the requests or the replies as events to downstream services. And where that could be potentially important would be, doing big data analytics, doing fraud detection, those kinds of things, where you want to see the actual requests that the user's making from a RESTful perspective, what the responses are, do correlation, all of those kinds of complex event processing type tasks. You're able to do that by extending the event broker, having the event broker actually proxy those REST APIs, turn those requests and responses into events, and then consume them in a zero to many sort of a mindset. And again, the nice thing is that these applications, they have no idea that essentially the event broker is being a proxy, just like they didn't really know that there was an API gateway in the loop. So it keeps you from having to add additional logic to your applications, turn up log levels, all of those kinds of things if you're basically just wanting to sniff those different requests and responses. And that's something that an event broker can do. From a Solace perspective, we actually call that functionality a micro gateway. All right, so let's talk about the one-to-many pattern. If you've used an event broker before, if you've used a messaging system before, this is probably fairly obvious to you. But essentially, what event brokers facilitate is one-to-many distribution using the publish and subscribe pattern. So let's say you have microservice A, microservice C, D, etc. Essentially, if he publishes an event through, for instance, JMS, he's going to get an acknowledgement that that message, again, was successfully persisted by the event broker so that it won't be lost. These other applications receive that event, and they can receive that event through different standard APIs or different protocols. So maybe microservice C is also written using JMS, so he receives the event. Maybe you're using Spring and Spring Cloud Streams to write your microservices. He could receive that same event. And what if you're using AMQP? Again, he could receive that event. They're able to process, though, completely out of band from each other. They're able to acknowledge those events asynchronously from each other. And ultimately, you have decoupling, again, from the different microservices themselves. And you actually have decoupling even from the underlying messaging API in wireline protocol that was used. And ultimately, you can even use this kind of pattern with something that isn't just a messaging API. So let's say that you have a microservice and he knows how to do HTTP posts. Well, he could actually post his request, get a 200 OK response, meaning that the event broker received the message, and then be able to basically do webhooks, again, Spring Cloud Streams, AMQP, whatever you want. But my point here being is that you can actually use HTTP and still be asynchronous, and the key enabling thing for that is the event broker. It's keeping track of who ultimately it needs to webhook that to, who it needs to be able to facilitate through messaging protocols or Spring Cloud Streams, etc. And the key is this is an example of something you would not want to build into your microservice, because essentially if you built it in, you're building an event broker and all the complexity therein into your microservice, which simply just doesn't make sense. Again, they're also finally able to acknowledge those messages asynchronously as needed. So to kind of conclude, here's the value summary, right? So again, you want loose coupling, you want one-to-many distribution, you want deferred execution, and you want reliable delivery, because ultimately, microservices require it in order to have the value that you're really looking for, right? The value that we're talking about here would be, the ability to add more functionality more quickly, more agility, all with low effort. You do want one-to-many distribution because from what we've seen, rarely is a piece of data only consumed once. I think that's a fallacy that's kind of exists within sometimes the API space. is that everything is kind of a one-to-one style interaction. You do want deferred execution from a response time, scalability, shock absorption perspective. And finally, again, a lot of microservices architectures today are using eventual consistency, which implies you need reliable delivery and you need to be tolerant to faults, speed mismatches, etc. So hopefully, you've now gone through the entire journey of understanding what our definition of microservices are. You understand the RESTful request reply paradox and where that should be, where REST can be used successfully, where it can't be used successfully, and how basically the best of breed solution is to combine microservices with events and APIs in order to have a scalable, reliable, and add agility back into microservices. So again, if you have any questions, please don't hesitate to reach out. Please visit us at our website at sols.com. We're interested to continue these kinds of conversations and look for future videos where we explain how you actually build these event-driven microservices using Spring and have them be event-driven. So stay tuned for that. Thank you for your time.